Maybe you can start. So today we have a seminar by Andrea De Luca from Cergy about monitored quantum systems, products of random matrices and permutations.
Okay, thanks, Guillaume. Thanks to the organizer for inviting me. It's a pleasure to be here. I've never been in Boston and Harvard. It's really a pleasure. And I'm enjoying this program quite a lot. So what I will be telling today starts as a motivation, we start in quantum system, quantum mechanics, so many body quantum system, in particular in monitor one, and I will explain what that means. And then it will naturally go to the realm of random matrices and products of random matrices in particular. And it will be we'll have some connection with the permutations and irreducible representation of permutations. So the two main articles that I will going to talk about today are these two, in particular this one, which is an article which came out a couple of years ago. It's not yet published, but contains most of the ideas. And then there is this other one, which I will probably only touch briefly, which essentially concerns about the continuous time version of this. So what I will tell you today is about discrete time, so products of matrices, and this is like stochastic processes, but it's a similar idea. So, okay, let me start by just explaining what we mean with monitor system. And so since this is probably a diverse audience, I will start talking about measurement in quantum mechanics. So probably this will be trivial for most of you, but I think it's useful to set the ground. Okay, so I will mainly talk about we talk about finite dimensional systems. So for me, my Hilbert space is some something like this, and in general, I will have in mind that Q is composed by what physicists call qubits, so it's some powers of 2, and essentially this means that this is just so many copies of C2. And okay, so when we write like this, then we know that unitary evolution means exactly what you can expect. Just that I can take any other. So I will be mainly concerned with states, which are just for me Q times Q Hermitian matrices. So for me, this is a state or a density matrix. And it has to be positive. And okay, normalization normally means that trace of rho is equal to 1. But in general, I will also have to use some unnormalized version of this. And as a notation, I will use the tilde to mean that it's not normalized. And you can always define normalized version by this. Okay, and so once we fix what's the state, unitary evolution just means that I can map state to another state just by doing this, where U is sign elements of OQ. Okay, so U, it's the unitary group, Q elements. Okay, so far it's good. So that's just about evolution. And then, okay, measurements is something which goes a little bit beyond the unitary evolution. It poses many conceptual problems, but for the moment we will just stick with what it means mathematically. So mathematically it means that I take some Hermitian matrix, O, Hermitian matrix, and I can consider its spectral decomposition, so something like this. I have some O lambda, lambda. So these are the projectors onto the eigenspaces of these operators. Then measuring an operator means that I will pick one of these guys, one of these eigenvalues, and the state evolves like this. So under measurements, it becomes something like normalized. Okay, so this is my new state, so lambda. And the probability for this to happen is exactly this denominator here. So with probability, which I can write as small p lambda, it's just this. Okay, so the fact that these measurement outcomes have a specific probability which depends on the state itself is an important ingredient in what I will say, and this is normally called Born rule. Okay, so this is the setup. Okay, okay. So what I want to do with this? So mainly, the idea is to study the repeated actions of some unitary dynamics and some measurement dynamics. So I will repeat these two operations. So generally, we can imagine a process like process where I take a unitary matrix, I apply it to rho, so it evolves like this, and then I will apply some projector. Of course, this needs to be normalized, but so U1, U2, and another projector, and so on and so forth. So this defines some repeated measurements.
Why do you want to make it alternate? I mean, you could run for a long time unitary and then you will measurement. In the formula, you alternate measurement and unitary, right?
So you're asking whether I could do all the measurement at the end?
Well, I mean, you could put the unitary to some power and then measure.
Well, I mean, these things do not commute in principle, right?
No, sure, they do not commute, but I mean.
So I have to do this in a certain order.
I mean, you put a UN, sorry, I actually didn't see the N. I mean, so the unitary time evolution goes for n steps, is that right? I mean, no.
I'm just taking some unitary matrix. I haven't specified what's the time. So I'm just alternating some unitary dynamics, some projection, unitary dynamics again. Okay. Okay, and to make things simple, I will imagine that my initial state is the so-called completely mixed density matrix, which just means that it's the identity appropriately normalized. So it's and okay, so the idea is that when I do this operation, which is a random one, because the measurement outcomes, as we discussed here, will be random, so I don't know exactly what will happen. Rho goes from being the identity, so a maximally ranked matrix, into typically a projector onto of rank 1, because I keep projecting, so I keep reducing the space. So this is, let's call this rho 0. So rho 0 is maximal rank. And I can expect that if I apply this many steps, so it becomes large. The question is how large, essentially. I will get something which has rank 1. Okay. So
I'm not sure I understand the rank 1. I mean, each measurement, I mean, you prescribe which one of the measured values you're actually. I mean,
so this typically are large spaces.
But yeah, no, I understand. But then you have to fix a sequence of A lambdas.
This is just one realization of this process.
One realization.
Yes, yes. So this will depend on the sequence. It's sequence dependent. But I essentially know that if I wait sufficiently, if I do this for sufficiently many steps, I will eventually reduce it to rank 1, irrespectively of the particular, with probability 1, say.
Hey, when you say sequence dependent, you mean dependent on the choices of the
Exactly.
UIs and the measurements?
Exactly. Yeah, exactly.
Is your claim that you always get the same rank 1 matrix, or you
No.
always get
Just the rank is 1. I'm not saying it's the same rank 1 matrix. Okay, I can probably erase here. Okay, so
I mean, your projections are already rank 1, but then the whole rank which you're using.
no, okay, this I should have specified. So of course, if this Hermitian operator is not degenerate, then it means these are already rank 1 and this happens in one step. But I will assume that these are typically, there is high degeneracy, so this typically, the rank of each of these is a fraction of my big Hilbert space. So in one step, I just reduce it up by a little bit, but I don't go to rank 1 immediately. Okay. Okay, so I would just say.
There is a line that you erased.
Oh, yes. Yes. Okay, so how to quantify this fact, how far I am? Okay, I will introduce a set of operators, a set of functionals, say. So the easiest one is what physicists call purity, which is nothing but so that trace. But let me sometimes they use some P2, something like trace of rho square. So just sum of the eigenvalue square. Now in this situation, so at time 0, okay, P2. All of these are the same, so the purity is 1 over Q, is the maximal one. Sorry, maximum, no, minimum. And when I reach a rank 1 projector, it means that all these guys are 0 but 1, which is exactly 1. So this equals to infinity. It will go to 1. Okay, so there will be some typical time scale which is required for this to happen essentially. So that's the basic idea. Okay, I think I can erase this.
It doesn't depend on which unit you find.
Yeah, I will explain what I mean with that. Yes, the claim is that it doesn't. Okay, so the first thing I would like to do is introduce what people call as Gauss operators. It's this, at this level, it's just namings, but which is just a compact way to encode the fact that I can do these two combined operations. So if I take this kind of projectors, which give me the identity, but I can also combine them with some unitary operations and define something like this. This defines some k of lambda. And the cross operators are such that this just gives me the identity. So instead of talking about the combined actions of choosing some projector and some unitary matrix, I will generally talk about a set of cross operators. You can always think of constructing them in this form by taking some set of projectors and applying some unitary operators. But in general, the only thing you need is this kind of decomposition, like this. And so essentially what I'm talking about is what I'm saying is that I'm applying at every step with this depending on specific lambda. Okay, so this is one step. And then there is the normalization. And this happens as before with probability, which is exactly okay. Okay, so generally speaking, beyond the purity, I could consider more general symmetric functions of my spectrum of the lambdas, small lambdas. Sorry, I have probably mixing notation. These lambdas have nothing to do with these lambdas. I'm sorry. These are just the spectrum of this density matrix. These are supposed to be, let me use some O here. These are just the eigenvalues of my operator. But this has nothing to do with lambda. Okay, so I can consider more generally any symmetric function of the lambdas. In particular, we'll have some useful objects will be symmetric polynomials, power law symmetric polynomials of the lambdas. And I will have in mind some mu, which is written as some partition. So generally will be some 1, 2, and 2, 3, and 3, so on and so forth. And when I write this just means product over I over lambda. Okay, let's use J. Right, so this is just definition of a symmetric power law symmetric polynomial with a given partition mu. So of course, what I call the purity corresponds to the simple case in this notation, just the partition with just of two elements. Okay, and the reason to do that is that this includes all possible moments of these guys. For instance, could consider powers of the purity, which are just p mu of the lambdas, when I've chosen mu to be 2 to the k. This is notation for partition. Okay, so this is just a partition of 2k. I shouldn't go there. Okay. Okay, so this is just set of names. Okay, now there is one important aspect that I need to discuss. It's the fact that measurements combine well under the repeated actions of this. What I mean with that, let me explain what I mean. So if I do one step of measurement, as I said before, what I'm doing is this operation here, normalizing with some probability, which is exactly this guy. And it's useful for me to introduce some unnormalized density matrix, which is nothing but the thing in the numerator. So that this can just be written as rho tilde lambda. Sorry, I said promise this should be all. Divided by the trace of rho tilde rho with probability, which is precisely the trace of this rho tilde of rho. Now, suppose I do another step. So I have to take now this new state here, which defines my rho, let's call it 1. So rho 1 goes into some k of O2, put the 1 here. Rho 1 k of O2 dagger.
I'm confused by the subscripts. And now rho tilde equals k lambda, blah, blah, blah. Should there be subscripts O1 in front of?
Yeah, so here there is a subscript everywhere, O1. This is the rho 1 unnormalized.
Okay.
Yeah. And now I'm saying I'm repeating this operation. So I'm doing another, I'm choosing now another eigenvalue, O2. Again, I'm normalizing. But this is nothing but normalizing the numerator. So what I could do is just take the original density that I had there, apply KO1, KO1, KO2, KO2, and normalize this. Okay.
The dagger sometimes on one side.
Not being consistent. Oh, sorry. Okay. Okay, it's not very important here, but yes, I'll try to be more consistent. Okay, and now the probability for this to happen is just the probability that this happened before, and then condition to this, you now use this denominator as new probability. But now the combined probability of measuring 1 and 2 is nothing but this denominator again. So it's exactly this. So with probability trace A02, A01, Rho0, K01 dagger, K02 dagger. So in this sense, what I mean with this is if I want to know what's the probability of the final outcome after many of these step of measurements, so I have the first, which gives me K01 rho, K01 dagger, 2 and dot dot. What I can say is that I will produce a row after all this sequence, say 1, 2, 3, sorry, which depends on O1, O2, which is nothing but the product of all these. 0, KO1, KO2, KOT, KO1 dagger, KOT, normalized. And the probability for all this sequence of measurement to happen is exactly this denominator. Okay. Okay, so why is this useful? It's useful because now if I want to average this kind of objects like this, what I have to do is simply use this kind of expression. So first of all, Q mu of lambda, by this definition, is nothing but the product over J of the traces of this row. I won't put all these indices, but okay. And now when I want to average this, I will have to compute the sum over all the possible measurement outcomes, which are these O's of this object itself. So okay, let me define by this P mu applied to the matrix itself. Now it becomes an operation on the matrix. Now I have just to include the probability of this for this to happen, which is nothing but trace of okay, let me define, sorry, I should have done this before. Please define the rho tilde 1 or 2 T divided by the trace of rho tilde. And this is just the trace of rho tilde. Okay. And now, since this guy here is homogeneous, I can just rewrite this in terms of rho tilde itself. So this just becomes sum over O. I have P mu of rho tilde. And this trace of rho tilde is taken to the power 1 minus mu. Okay. That clear so far?
What is the sum of all?
I'm summing all possible measurement outcomes here. So that's the random process that I want to do. Okay. Okay, so why is this useful? Okay, now we'll do something that physicists like a lot, mathematicians a little bit less. So now this object is not so nice for us because it contains some denominators in general, because this mu, the number of mu is generally larger than 1. For instance, in the case of the purity, this was 2. So this is something which is naturally a denominator. So what I will do is introduce some different kind of expectation, which depends some integer n, or actually depends on some parameter n, which for the moment is not an integer, but which is this expectation of this p mu of rho, which by definition I write it as this sum mu of rho tilde, and here I will put n minus mu. Okay, so in principle, I will recover this formula if n goes to 1. Okay. Okay, why is this useful? Because I can look at all this guy now, again as a symmetric polynomial, but with an extended partition which contains n minus mu fixed points, essentially. So I can define mu n, which is, I don't know what's the right notation for this, but it's this mu. Oh, let's do an example, it's simple. So suppose mu was like 2 to the k, and I define mu n as 2 to the k, 1, and minus 2k. Okay, so in this way, I have now naturally rewritten this. Actually, go here. As some row of p mu n rho tilde.
Right, so that Albert equality is by definition, that's what the symbol superscript n means.
Yes. Yeah, that's the definition. Okay. Okay, so far so good. Now, the nice thing is that in this kind of new process that I've defined, where I'm averaging this kind of different power law symmetric polynomials, which have been extended to have always degree n, I'm directly summing over all the measurement outcomes, and I don't need to care about weighting the measurement outcomes with some particular weight, because the weight has essentially been included in the quantity I want to average. Okay? So that's the great advantage. And now what I will do now is, okay, I will simplify a little bit now my model to make calculations easier. And I will try to claim eventually that this doesn't depend on the specific details. So what I will do now is saying that this k of O is Krauss operators I will take them as just Gaussian random matrices. Okay, this is a big simplification, but eventually I will try to argue that it doesn't matter too much for what I want to discuss. So the calculation I want to do now is has been reduced essentially to this game. I take rho, which is initially the identity. I don't care about normalization because this guy is not normalized. And I define some rho t as the product of k so this is my rho hat. And then I want to compute. Now, the expectation value I want to compute is now on this simpler process, which is just multiplication of random matrices. So please define E naught of E mu of these four hats. And now this just means averaging over the measure of A being random matrices, Gaussian random matrices.
The original class operators were low rank, right? They were unitary times projector. Here, your random matrices are full rank, but you're claiming that for your purposes, this doesn't really matter.
Yeah, I mean, I could do a slightly more complicated model where truly these are written as unitary times projectors. This will make a calculation a little bit more complicated, but eventually it doesn't play a big role.
Nice.
The important part is that these are non-Hermitian operators. So they will project anyhow, essentially. Okay, so okay, now this is the quantity I want to deal with. And just a comment here, I said that my original problem, which is measurements, is the case where I take this n equal to 1. This is the so-called Born rule, because this 1 originally come from the fact that I want to give a weight to each measurement outcome, which is the trace of my state. So this is Born rule. For a more random metrics perspective, this is just an extra piece, which doesn't make much sense from that point of view, but it still makes sense to consider the product of many random matrices and look at the distribution of the normalized singular values, which is what I'm doing. So that will correspond to the n equals 0 case. So these are just singular values, or let's say normalized singular values, such that their sum is 1 of the product of random matrices. So both this problem can be treated in a similar way if I can study this for generic n. Okay.
Sorry, what quantity are you computing about the singular values? The sum of square.
Okay, I can actually compute. I'm discussing here a formula which treats any symmetric function. In particular, I'm focusing on symmetric, power law symmetric polynomials.
Okay. Just some symmetric function.
Yeah,
with
okay.
singular values.
That's a good point, actually. Okay, more specifically, I think some interesting quantities that people look at are some sort of entropies. So, okay, they are normally one way to define them is you write them as this is just sum over lambda I to the n. In other words, I'm just saying that this Sn as function of the lambda is defined as 1 over 1 minus n. Okay. So these are normally called parentheses Rényi entropies. And one reason to introduce them is that if you take the limits n to 1, you just recall the usual Shannon entropy say, so which is okay. But the reason to write it in this form is that now the moments of this quantity are this p mu lambdas. If I take mu to be n to the k. Okay, so I can express all the moments of these entropies in terms of power law symmetric polynomials. Okay, now I will try to explain to you what's the formulas that we use and to compute this kind of objects. And I mean, of course, you can treat this problem with more standard tools of random matrix theory by trying to write the spectrum of all this quantity, but I will argue that it's useful to work with the replica space in a sense. And to do that, I will use some diagrammatic notation. Okay, so
So for you, I mean,
yes.
I don't have a very good picture of what these random matrices actually are. I mean, they are fully occupied. I mean,
Yes.
And
Generally,
I mean,
yes.
they look like GUE random matrices, or what? I mean,
Well, that depends on which stage of this process you are, because they start like the identity and they end up like a projector. So in the middle, they will have a rank, which is somewhere there. So essentially, they look like projector on a space which restricts more and more, and inside the space, they look like random matrices. Like
When you say they look more like a projector, the rank is not actually going down. You just mean that there are some eigenspaces or some spaces where the singular values are very, very
the
small.
rank is actually going down because
Even
what
in
happens?
Gaussian case.
Yes, because what happens when you keep multiplying is that the eigenvalues of the unnormalized matrix grow. And one of these guys will grow faster than the others.
Right.
So when I
Yeah,
normalize, I
some
will
of the eigenvalues get very small, but they're never actually zero, right? They're just going to zero.
No, but I'm normalizing, so the maximal one will win.
Oh, I see. Okay.
I mean,
yeah,
okay,
yeah,
that's a good point. So if I think at the spectrum of the intuitively to say that if I think at the spectrum of this guy, this has some lambdas, which are not the same lambdas we're talking about because these are not normalized, but these typically grow exponentially with some index here. So there is some lambda, let's write lambda I. And when you normalize, clearly the sum is dominated by the bigger one.
Okay, thanks.
Okay, so that's why when t is large, this becomes a projector. Okay, so so I want to define some graphical way to denote this. So to do this, the main idea is that when I write this kind of object, so let's look, for instance, at this trace of rho tilde square. I can see these as an object which lives in the space of the tensor product of two of these copies. So let's write this as times an operator which swap the two. So probably this is clear if I use some diagrammatic way to write this. So this will represent one of my rho tilde. This represents the other one. And tracing in this language just means closing this leg with that. So if I do nothing, I just get trace of rho tilde square. But here, if I swap these two, then close, this produces exactly trace of rho tilde square, okay? And in general, I can write any of this symmetric, Pavlov symmetric polynomial of rho tilde as some trace, say that this is degree n, as some trace defined in a tensor product of n copies. If I put the appropriate operator here, let me define a mu, which swaps the copies in an appropriate way to reproduce the object there. So let me, probably an example would be useful here. Using the same notation as before, I have rho here, rho, many copies of here, this, then I want to close this like this to compute all these traces. And here I'm putting some operator, which I'm calling a mu, which is just a permutation of all these legs, such that this will produce. Will produce precisely the symmetric polynomial that I have there. And in order for this to happen, a mu must act as a permutation in the n copies of my Hilbert space. So this rho is defined, I call the Hilbert space like this. So this be an operator in this space. And the permutation has to have a cycle decomposition, which is exactly mu. So cycle decomposition. Is this clear? I can do another example, but essentially the logic is exactly this. So suppose you want to get row cube, you just do a cycle of length 3, and that produces row. Right? You just follow this line, and this will do row, and okay. We'll do as many rows as the length of the cycle. Okay, so far so good. And this helps me to do this kind of representation for this whole process. So in this language, let me, I use this representation like this for row, but let me now fold a little bit this line, and so I will use this kind of representation for the two legs. So this is what I was calling row before. And now let me use some notation for K and K dagger. This. So this is just one time step. So this is supposed to be K, 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 and each of these is supposed to be K dagger, K dagger, K dagger. I'm just multiplying on the left by K and on the right by K dagger. Right. And when I do this again, I will have another of these rectangles. Again with that. Okay. And when I finish this, since I want to compute this P mu, I'll have to put my operator P mu. Okay. So this notation is just a way to represent P mu of rho f. Assuming that rho tilde, assuming that rho tilde is some product of K, K, K. Here there are just two, let's say K1, K2, rho 0, K1 dagger, K2 dagger. Okay, so this is just an example with 2 steps. Okay, now here it comes an important point, which is now I take the Gaussian average of these matrices. I assume them to be Gaussian. When I take the Gaussian average, I can use big theorem, essentially, which means that I have defined all the possible contractions of these legs, well, essentially the orange one with the violet one. So just to give you the explanation with just 2. Suppose I want to do expectation value of this on this K. Okay, there will be a factor which is just the variance of these matrices, and there are as many as the number of copies, which in this case is 2, so it's sigma to the 4th. And then I will have 2 terms, which are nothing but okay. So I'm just using big theorem to say that this has to be the same as this or the same as this. Right? So this is just application of big theorem for Gaussian matrices. Is this clear?
Well, it's not clear. Why can you assume Gaussian? I mean, some central limit theorem is acting here. Or why can you assume that the distribution is Gaussian?
Oh, this is just my hypothesis.
It's a new model.
Yeah. I say that in this model, I'm taking the K to be Gaussian. Yeah. No. Without that, that's not that simple, but. Okay, so more generally, if I have more than 2 copies, this just translates into. So what I'm simply saying here is that if I do the expectation of a certain set of k's, n copies of k and n copies of k dagger, in this kind of notation, this will give me sigma to n, which is just the variance of these matrices, and then I have the sum. Sigma is not a good name now. Okay, let's use pi. In the permutation group of something which I can write like this.
All right. To the right of this.
Oh, sorry, I did it again. I'm sorry. Okay, so we have sum overall permutation in Sn. And in this graphical notation, I will have this permutation pi. The same permutation here. Okay, so this is just application of Wick theorem. And now notice that if I start from the identity, this is if rho 0 is the identity. In this kind of notation here, I have nothing. This is just the identity matrix. So all this is nothing but the identity itself in this kind of notation here. So all this kind of Gaussian averaging, I do this E naught of this P mu of rho tilde, I can rewrite it as sum over pi 1, pi 2, pi t, all in Sn, of this kind of graphical object where I have some A mu, have some legs, I have some pi t, I have pi t, pi t minus 1, up to pi 1 identity. Okay, I'm just using that each of these pieces can be written as this. So I'm inserting each of these spaces a sum over the permutation group of this kind of operators, and I get this kind of products here, scalar products. Okay? Okay, so the fundamental object here, as you can see, which appears many times, is essentially this kind of contraction between an element of the permutation group, call it pi, and another element of the permutation group. So I can define a matrix like this, which depends on pi and pi prime, like this. And okay, if you think a little bit, this matrix eventually just counts the number of loops in the products of these two guys. So okay, let me first write it and then I will try to justify it a little bit better. So this will just be Q, the number of cycles of pi prime minus 1. So to see that, okay, let's do a simple case, which is just say pi being the identity. So in that case, I'm just doing a case where these are just closed like this. And this, for the same reason as before, okay, let's do one example. Say, let's do for n equal to 2. And I have just 2 of this. So I have either this, and each of this factor gives me a trace of the Hilbert space. So it will give me a Q here and a Q here, so a Q squared. Or if this one is the swap, I only have a single type. So generally speaking, this matrix counts the number of cycles. Right? And another way to rewrite this is by saying that this is n minus the distance between pi and pi prime, where this is the transposition distance between the two permutations. Is this clear? I mean, it's just a standard identity that the number of cycles is n minus the distance. Okay, good. So essentially, we found that the expectation value of this t mu can be written as the powers of this matrix T to the power T. It's the number of time steps that I'm doing. And then I have to take the matrix element between, okay, the final transposition, the final permutation, which has to be in the conjugacy class of mu, which is what I want to compute. And I start from the identity. Okay? So it's just a matrix element of this kind of Hopin matrix in the permutation group. Okay, and now it comes why the details of this problem are not very important, and I can claim that these formulas end up being universal in some regime. So the point is that this matrix typically wants pi and pi prime to be as close as possible between them, because it costs more and more in terms of powers of q to have them far away. So the leading term will be when, of course, there is the leading term where they don't change at all, which is pi equal pi prime. So this is just some factor q to the n. Then there is the identity, so let me use this pi prime. I have the identity. And the first correction to the identity is going to be and A is the adjacency matrix of the transposition graph. So it puts a 1 only if pi and pi prime differ by one single transposition. Now the point is that if I take another model, generally speaking, it will have different subleading corrections here. But the first one is always going to be transposition, because that's the easiest way to connect to permutation. And so if I consider now the following scaling limit, I want to consider a limit where both the size of this matrix, which is Q, is large, but also the number of these matrices is large, but in such a way that the ratio is kept fixed. Then let's ignore for a moment this factor because this will disappear in normalizations, but essentially this T to the T converges to 1 plus A over Q to the T, just means is this okay? And this scaling limit I can define in many different models, which go beyond the Gaussian one I'm considering here. And as long as the first term is just the adjacency matrix of the transposition graph, this will happen. Okay? So that means that I will use this kind of equivalence to refer to the scaling limit. So this has become e to the xa between some permutation in the conjugacy class of mu and the identity. Right? And this defines a set of functions in this scaling limit, which depends on this single variable x and on the particular observable that I decided to look at, the particular symmetric polynomial of this, which I'm considering. Now, the first question you can ask is now, how do you handle the problem of taking the limit n to 1 or n to 0? Because now I'm working with a permutation group of which is Sn. So how do you take this limit? So these objects are well defined as long as n is an integer and is an integer larger than Italy. Okay, so the first thing you can do is look at this kind of these quantities perturbatively small x. So let's do one example, for instance, which are, I call the purity, the powers, the moments of the purity as this lambda I square to the k, and which means that this mu extended has to be 2k 1 n minus 2k. So I will try to explain graphically what I want to do. So clearly, if I start to expand this in powers of x, I will not be able to connect in any possible way the identity with this kind of, with a permutation in this conjugacy class, unless I go to a degree which is as large as the distance between these two. So what I'm trying to say here is that if I expand this in small x, this is at least x to the distance between mu and identity. Because I need at least as many powers of A, which means as many transpositions to connect the identity to this mu. And so in this particular example here, since I'm taking mu, which is exactly composed by k transpositions, I'm already telling you that this starts like x to the k, independently of n. So okay, this factor is the easy one. And now additional corrections are a little bit more complicated, but I can claim that they are always polynomial in this n, so they can be computed. So I will just show a picture here. I think it's is it working? No. Okay, so I'm just using this graphical representation now to refer to this plot here. I'm just referring these lines as transpositions. So suppose I want to connect the identity with a given set of transpositions, I have to insert, the minimal case that I can do is inserting as many transpositions as I need to reach the final state. Now, subleading terms here are giving when I insert more transpositions than the minimal number I need. So there are different ways to insert these transpositions. So the simplest case is where I insert these transpositions connecting the n minus 2k fixed points that I wasn't using before. So these are the 2k elements on which I'm acting with my transpositions, and this one are the additional ones. And so since I can choose among, so I mean, just to clarify, I'm just saying that if I consider a transposition like this, I can write these objects like 1, 2, 3, 4, 5, 6, so on and so forth. And then I have all these parts which are fixed points, which start from 2k plus 1 up to n. Right? Okay, all these are fixed. And then I'm saying whenever I can insert a transpositions which swaps two of these elements and then put them back. And this can be done clearly in n minus 2k, choose two ways. So this is a polynomial object in n. So I can take the limit. And all these other cases, I mean, I won't go into the details to kill you, not to kill you, but all these are the other possible ways to count in how many ways you can put these extra transpositions in this kind of path. And if you account for all of them, let me just, you can get the corrections to do to this purity, and in particular to its log, which is what I'm calling S2. So this is just some numerics that I've done very quickly. So the orange and blue dots are two examples of coming from numerics with random matrices done in this scaling limit where you see they collapse. They come from different ensembles. One is a Gaussian one is not a non-Gaussian one. And you see they go one on top of the other. And the curves that I'm showing you are increasing approximation obtained, adding more and more orders in this kind of expansion at small x. And so you can see that you get, so the main problem here is that these kind of expansions are just asymptotic. So the more order you put, the worse it gets. Unless you are...
Isn't the red one better? Have you mislabeled?
Unfortunately not. The red one is the lowest possible order, and the higher order improve at very small x, but get worse. Graphically, you see them worse because it's asymptotic expansion. That's what I mean, yes. So, I mean, you do a lot of work to compute all these kinds of conditions, and then you plot it and... Okay, so in principle, you would like to resum all this. And actually, since now it's a bit late, I won't bother you how to do that, but you can actually do in some particular case, which is the calculation of the von Neumann entropy. So in this case, we got a formula in terms of some limiting determinants of bigger and bigger matrices, and eventually you get a curve which works pretty well. So it's this kind of, these are the data, and these dots here come from the analytical curve, which still needs to be computed semi-numerically. And you see they work pretty well. Okay, so this was just to tell you that there is a whole family of functions that one could try to compute, which are actually not super easy to access. You can compute them perturbatively, as I showed, but okay, there is the disadvantage that convergence is quite bad. And in some particular cases, we develop some technique to compute them, but generally, I think this is pretty interesting because I mean there is a large class of multiplicative processes in random matrices, which leads to the same universal set of functions. And so, okay, this I can stop. Thank you.
Yep.
So the early part of the talk, I mean, you had your Gauss operators.
Yeah.
I mean, this relies on the fact that you, in some sense, you know, you make a model in discrete time. I mean, you know, you do one step, the next step, next step. You know, but what one could do instead of the Gauss, I mean, you take a Lindbladian and then you get sort of like a continuous time model. Is that something which is of interest? I mean,
yes, okay, this was for the second part of my talk, but it would need another lecture.
okay.
So you can consider the continuous limit. So in the continuous limit, essentially, okay, the Lindbladian would emerge if you average over the measurement outcomes immediately. So without taking, so it would work, the Lindbladian description would work if I take objects which are defined by this kind of average. So this admits in the continuous limit some Lindblad description. But in generally, these kind of entropies that I'm discussing here live in some replica space where you have to take more copies of this. So generally the Limbladian is not enough, but nonetheless there is some possibility to define a continuous limit. Essentially, instead of doing what I was doing, which is this, you replace this with some finitesimal random matrix. And this will eventually describe a flow of the spectrum. So it looks very similar to Dyson Brownian motion. And you can show that there is a similar scaling limit where they give exactly the same formula that I got in the discrete case. So the continuum discrete give the same if you take the scaling limit.
Thank you.